So welcome everybody. This is the second advanced topics of the last marking period. Now you notice this word equilibrium, so we're going back to something that you guys already know something about, but we're being quantitative, not just qualitative. To put your minds at ease, this thing called KEQ used to be part of the regular course. They got rid of a lot of quantitative stuff. But just to show you that at root, it's not difficult. The skill itself is not bad at all. KQ is called the equilibrium constant. It is essentially the ratio of product concentrations to reactant. Notice that I crossed that out in yours. So essentially what you're doing is you're taking the concentration of the products and you're dividing it by the concentration of the reactants. That's a simplification, but it gets the point across. You may also see KEQ expressed in different forms. If you see Ka or Kb or KSP, it's all the same thing, specific scenarios, but all are expressing this the ratio of products to the ratio of reactants. And as a colleague pointed out to me, it's like alphabetical order going down. P comes before R. First you write the P, then you write the R. Right, Kelly?
Yeah.
Thank you. That's Sean Kelly, everybody.
No, it's Calais.
Calais, sorry. Guys, KQ is written from the perspective of the forward reaction. Okay. So that means you could, if you reversed it, you would have the information for the reverse reaction. Now it turns out products and reactants only in the gas and aqueous phase are included in the calculation of KEQ. We're going to create something called an equilibrium expression. We'll talk more about that in a moment. And the only things that have concentrations can be inputted into the equilibrium expression. So only gases and aqueous have concentrations. Solid has no concentration. Liquids have no concentrations. In fact, when you calculate KEQ, and if it's greater than 1, very simply, that means that the forward reaction is favored under those conditions. If, however, KEQ is less than 1, well, in that case, the reverse reaction is favored. Just to give you a little bit more extra information about this. Let me hit pause for a moment. Welcome back. So obviously, it was an inside joke. Key 1. Now, the first thing they're going to give you a reaction at equilibrium. Notice the double opposite arrows. And we want to write the equilibrium constant expression for it. That sounds tricky, but in reality, what did I say? It's just the ratio of the products to the ratio of the products to the reactants. Meaning, you put your products on top, right? And you put your reactants downstairs. Now, there's a little bit more to it than that. But that's essentially what it is. So let's start with the products. So we say the following, KEQ equals. Sometimes students just write the expression, but they don't say what it's equal to. Just I want you to know that we're calculating KEQ right now. We put the products upstairs. The products are H2S. What do we do with the 2, Colette? Well, we do the following. I write these square brackets. Square brackets means concentration.
Then you write 2.
Oh, hello. How are you? Old friends. What do I do with the 2? The 2 becomes an exponent. So the coefficient becomes an exponent. What goes downstairs? Well, the reactants. So I put the concentration of sulfur gas times the concentration of hydrogen gas. What do I do with the 2, class? It becomes the exponent. There we go. Guys, that's an equilibrium expression. Is that difficult?
Is that actually?
That's part 1. What's part 2? Well, that's just the significance. We simply have to multiply. Just accept that it's multiplication. My friends, to calculate KEQ, I have to give you equilibrium concentrations. Concentrations concentrations, concentrations. Notice you have to be moles per liter in order to do this. If I just gave you moles, you'd have to find liters so that you could then find what moles per liter is. In other words, you're not just plugging in moles here, you're plugging in moles per liter. Okay, but all we do now, my friends, is we plug in these three values into the equilibrium expression. So, KEQ, so H2S, just be careful, is 0.05 squared, divided by H2, sorry, let's go in the order, S2 is 0.3 by itself, times the other term, 2.16 squared. Okay? Now, yes?
Will they always give you the moles per liter?
They'll give you the mole, in this case, yes. If we want to find the KQ, they will have to give you moles per liter. Or guys, maybe they'll do it to you this way. They'll say 4.32 moles in a 2-liter container. You'd have to then have the presence of mind to divide 4.32 by 2. Okay? But yes. Okay? When I solve for that, guys, just because I have limited time here, KQ comes out to be, I think, 0.18. And interestingly enough, there are no units, which is going to make you happy because you guys don't ever write units anyway. So you're like, oh, this is like for us. Yeah, it's great. Kidding. Yes. 0.001. Could you guys check my math? Can someone check my math here? Here, I'm going to hit pause. Welcome back. Guys, I was verified thanks to the students in the room. It is 0.18. Again, what that means is that that reaction is less than 1, meaning that the reverse reaction tends to be favored over the forward reaction. Again, just a little bit more background into it. What else can we do with this? Well, P2. Consider the following dissociation of a salt into ions. Look what they give us. Oh, remember KSP is the same thing as KEQ. This time they give it to us. So that means instead of solving for KEQ, I'm going to be plugging KEQ into my equilibrium expression and then calculating a concentration. It's kind of the reverse from before. Well, the first thing we have to do is we have to create our equilibrium expression. Remember, it's products over reactants. I'm going to write KSP. Remember, that's the same blessed thing as KEQ. The products are on top. This looks pretty easy. I have the concentration of Ag. Notice a coefficient of 1, so that's unaffected. And then I have the concentration of its brother, iodine. Now here's something interesting. My friends, notice that's solid. Solid has no concentration. So I do not put this into the equation. At most, I can put the number 1 there. So you only put in species that are aqueous or gaseous. If you see solid, it doesn't go into the equilibrium expression. If you see liquid, it does not go into the equilibrium expression because they do not have concentrations.
They never go in?
Never, never. Okay, so that would be a correct equilibrium expression. Well, let's plug some values in. They tell us that the KSP is 8.53 times 10 to the negative 17. Let's plug that in, 8.53 times 10 to the negative 17. Now, we want to find out what the concentration of the silver ion is. I don't know what the concentration of the silver ion is. Do I know what the concentration of the iodide ion is? You see it anywhere? No, it's not there. Mr. Segalka, there's a problem in the question. Why do you say that? You can't have 2 unknowns. Well, it turns out we only have 1 unknown. It's true we're solving for Ag, so we're going to call that X. But remember, every time one of these breaks up, I break up into equal quantities of Ag and I. So class, if Ag is X, what does that mean about I? Oh, very nice. Eli gave me the X. Very good. Guys, what's X times X? X squared. Very good. So guys, it's the KSP equals X squared. So that means I have to take the square root of the KSP. Guys, I already did that, and I'm positive I have this one right. The concentration of Ag ions is 9.24 times 10 to the negative 9. And this is a concentration, so you do need your units. Big M, or moles per liter. Guys, that's really the unit. That's the task. What do you think? It's not too bad, is it? So I guess, oh, we're short. That's good. Could everyone say goodbye to the viewing audience?
Bye.
Bye.
Little under enthusiastic, but it's cloudy today. Okay, hopefully when you watch this, it'll be sunny outside.
I'll see you again.
Well, I'll see you again on the next day 5, right? Okay. Bye-bye.